Right. So as I was saying, I have been doing radiative MHD star spot simulations, and now I'm as Sven was saying before, talking about forward modeling from these MHD simulations. So I've been doing star spot simulations, and I've been also engaging in some forward modeling. So because of the short nature of the talk, I won't get into the detailed physics of star spots. I'll just present the results very briefly. So here you see star spots on the spectral types G, 2K, and M. And we found out that the contrast has a very strong dependence on spectral type. And so, for example, the M star has the lowest contrast, where the G star has the highest contrast. And then in our paper, we also calculated star spot temperatures with spectral type. And then I'll upload the slides, and I've provided the link to the paper. So in case you're interested in finding star spot temperature with spectral type, the data is available. And you can also we have calculated umbral temperature and penumbral temperature and quasar temperature at different tau heights. Now, what about star spot contrast? So in the paper that I showed you, we have calculated the bolometric intensity contrast, but we are also now calculating spot contrast at different viewing angles at different wavelengths. So for example, here I show it. So we have our MHD boxes, and then we calculate we shoot rays at different viewing angles, and then we calculate the contrast with respect to the local quiet star. And these are some preliminary results. So the basic result is that the contrast of the spot with respect to its local quiet star doesn't really vary with the viewing angle. So if you know the contrast of a spot with respect to its surroundings at the disk center, you would more or less, it would be a fair assumption to assume that it stays the same when a spot moves towards the length. So here I'm just showing the contrast at specific intensity, at specific wavelengths, but in the future we also plan to calculate this contrast over the full spectrum. And now I'll move on to some forward modeling. So a way of detecting exoplanets is measuring the wobble of a star. When a planet is orbiting a star, because of gravitational attraction, it will cause the host star to wobble, and you can measure the wobble and you can detect an exoplanet. But we must be careful because there are the stellar surface properties can also affect the spectral lines and can induce Doppler shifts. So I've listed here a few ways star spots can affect the radial velocity of a star. So the most basic way, or the simplest way it can affect, is by reducing the flux. So let's say, for example, on the left hemisphere you have a spot. It will reduce the flux coming from that hemisphere, and let's say the left side is coming towards you, then it will induce a redshift because you will have more flux from the other side. We also know that stars have a net convective blue shift because the in the granules, the upflow regions are brighter, they have a larger area, and therefore you have a net upflow. And if you have the presence of a spot or an active region, that would inhibit the convection, and therefore it would also affect convective blue shift. And so the first one has been widely studied. The second one has been studied to some extent, but what has never been considered so far is that spots and plages also develop their own flow systems. For example, ever-shaped flows and mode flows. And especially, for example, if you have a spot towards the limb, the ever-shaped flow will gain a line of sight component, and it can affect your radial velocity. And there's also a subtle effect that when a spot moves across the disk, the shape of the spot changes. For example, the disk side penumbra looks different, and all these effects will have very subtle effects on the radial velocity. So here I've listed two papers where they have attempted using MHD simulations and synthetic spectral lines to sort of answer these questions, but none of these simulations included spots. They were only confined to hydrodynamic and plot simulations. So now we have realistic simulations on spots on different spectral types. So here is an example of a spot on a solar-like star. This is a simulation. So the method that I'm following is, first I'm doing a non-radiative MHD simulation. So here on the left you see a sunspot at the disk center, and then I do calculate the Stokes profiles at the disk center, and then I tilt my simulation box, and then I calculate my Stokes profile again at different viewing angles. So for example, you can see here, this is a spot at 60 degrees, and the foreshortening of the penumbra that I was talking about is automatically visible here. And here I've shown you some, on the right, some example profiles of Stokes profiles of large and facular region. And you can see, so the dashed lines are quiet sun and the solid lines are plage. And you can see as you're moving towards the disk center, your faculae become brighter than your quiet sun. And so all of these effects are intrinsically taken care of, limb darkening, facular brightness, because we are doing the full MHD simulations plus calculating the Stokes profiles. So now how can we calculate disk integrate profiles from our simulation? So I construct a grid like this, and then so there are basically two things going on. One is your limb darkening, and your line profile is broadening as you move towards the edge, no matter which direction you go. And then if you have rotation, then depending on the location of the star, you would have a Doppler shift. So I take my profiles at different disk locations, and based on which location on the grid I place them, I give them a Doppler shift. For example, here I show you a blue shifted profile and a red shifted profile, and there is one at the center which is not shifted. And as you can see again, that limb darkening and line profile broadening has automatically been taken care of. So I'll show you some basic results. So first, simply without rotation, I take a star and a solar like star, and then I calculate. So this is no spots, no plages, just I calculate the bisector by integrating assuming a star which is just white granulation, and then I put in a spot at 0, 30, and 60 degrees. And this is without rotation. So any effect that you would see is purely because of the suppression of convection and because of the internal flows of the spots, and not because of the loss of flux.
2
So
minutes.
what you see here is very interesting. So I've tried out spots with different filling factors. So at 5%, so on the leftmost you have the disk center, then you have 30, and then you have 60 degrees. So obviously when you have a spot that is 5%, it has the most effect. So that induces a shift of around, redshift of around 15 to 16 meter per second. And then you move to 30 degrees and the redshift decreases. And something very interesting happens when you move to 60 degrees is when you have the spot 5% spot at 60 degrees, it actually adds to the convective blue shift. And again, remember, this is not because of the change in flux, but because there is no rotation here, but simply because of the internal flows and the suppression of convection. And now I add some rotation, and then when you have rotation, so the effects become a lot more pronounced. So here are some bisectors. So in the middle, you have 100% granulation, and then the green line is a spot with 5% filling factor, 60 degree west, and then the red line is a 5% spot, 60 degree east. And then you see that it increases to around 50 meter per second, the effect of the spot on the radial velocity. And for comparison, I have shown you here on the table a planet, how much planets of different masses will have an effect on the radial velocity of a solar mass star. And as you can see, even small spots can have significant effects. So I want to leave you with two messages here. One is that spots in active regions they have complicated physics, they have internal flow structures, and they have never been considered so far, and they can have significant effect on the convective blue shift of a star. And the second, now that we have this radiative MHD plus synthetic spectral lines, we can actually study, we can make up different spot facultative configurations and study the effect of different configurations on the net RV. Thank you.
Thank you very much. So there is a question on Slido. How does the size of a spot depend on the spectral type for a given amount of flux?
So the thing is, the size of the spot that I'm choosing is basically a free parameter. I mean, because I'm doing local box simulations, the size of the spot is something that I don't determine, that I determine myself. And so I basically put in flux tubes of a certain size. So I still have to, yeah, basically the size is a free parameter in my simulations.
Okay, yeah, thank you.